I'm Jonathan Aldrich. Let's put our architecture hat on and talk about compiling for modern processors. A key consideration for compiling programs for modern processors for high performance is reducing pipeline stalls. Now, pipeline stalls are caused by four main problems. One is a cache miss. So a load or a fetch of an instruction may miss in the cache, and we have to go to main memory to get that data or that instruction. That takes a long time, and so we stall the pipeline until we get that data or instruction. Resource hazards happen when we have two concurrently executing instructions, and they need to use the same functional unit at the same time. If we have only one functional unit, one of them has to wait. A data hazard happens when one instruction needs an operand that hasn't been produced by an earlier instruction that maybe is still executing. Perhaps the earlier instruction is stalled, and so we can't get the result yet. Or maybe it is executing, but it takes us another pipeline stage or two before we can get the data from that previous instruction to this one. Finally, there are control hazards. Until we know the outcome and the target of a branch instruction, the processor doesn't know where to fetch these subsequent instructions. We can reduce these stalls with a variety of different hardware mechanisms. All of these strategies can speed up processors, but they all cost resources and therefore are limited. We can't invest unlimited resources in things like caches. If cache misses are a problem, we can make caches larger so that we hit more often. We can also add associativity. So if two cache lines, if two parts of memory are mapped to the same line in the cache, then if we have an associativity of 1, then every time we access one, it'll kick the other one out of the cache. And so we won't get benefit from the cache if we alternate between accessing those two cache lines. On the other hand, if we add associativity, then we can allow two lines that would map to the same place in the cache to coexist in the cache. That would be an associativity of 2. And we could also have associativity of, for example, 4. Beyond that, it gets too expensive because we have to manage all the different cache lines that could be associated in a particular place. Resource hazards can be addressed by adding multiple copies of functional units. So let's have two adders or two floating point units. That will allow two different computations of the same type to execute simultaneously. If we have a miss, a resource, or a data hazard, we can execute instructions out of order so that future instructions don't have to wait until after a stall. Finally, for control hazards, we can predict the branch destination and execute speculatively, and then undo things if we're wrong. Now, these techniques can reduce stalls, but they don't eliminate them. We can reduce them further by being careful about the way that we schedule instructions in our compiler. So for example, for an in-order processor, some instructions might take more than one cycle. A load typically will take more than one cycle, even when it hits in the L1 cache. Some slower floating point operations are also likely to take more than one cycle. So what we can do is schedule other independent instructions between the slow instruction and the instructions that need its result. So for example, let's look at this program. Here we're adding R1 and R2, storing it in R2. We're loading A into R3, and then we're adding R2 to R3. In this example, the load of A is used by the very next instruction. And so there is likely to be a processor stall. We can avoid that stall by moving the load earlier so that we load A into R3, and then we do the add of R1 and R2, which is totally independent of the load. And then hopefully by the time we get to the next instruction, which actually uses R3, the data will be there. Now, this is for in-order processors. For out-of-order processors, the hardware can do the instruction reordering on its own within a limited window. So we don't have to be so careful about scheduling instructions so that they don't conflict. However, it's important in instruction scheduling to maximize instruction-level parallelism. Basically, we want to always have a lot of different unrelated instructions available in the instruction stream so that the hardware is able to actually reorder them to address any stalls that happen. In order to maximize instruction-level parallelism, we have to reorder instructions. And reordering instructions has to represent dependencies between those instructions. In general, there are three different kinds of dependencies between instructions. The first is called flow dependence, or read after write. This happens when a later instruction uses a value that's produced by another early instruction. So this is a very intuitive form of dependencies. And this is called a true dependence for that reason. An anti-dependence, or a write after read, happens when a later instruction overwrites a value read by an earlier instruction. So we can't move the writing instruction above the reading instruction because then we'll read the wrong value. So for example, in the code here, anti-dependencies on register R1 make it impossible to move two instructions after the load, right? We'd like to move this R3 gets R1 plus 3 down below the load, but we can't do that because of an anti-dependence. And furthermore, we'd like to move the instruction at the bottom up so that it, again, can be between the load and the thing that it uses. But that's also not movable because the previous instruction reads R1, and so we can't move the write above that. An output dependence, or write after write, happens when a later instruction overwrites a value that's written by an earlier instruction. So again, we can't change the order of them because then we'll be left with the wrong value in the register. It turns out we can use techniques called register renaming to eliminate both anti and output dependencies. It doesn't help with true dependencies, but it can get rid of the others. So for example, in the example that I showed you before, instead of using register R3, which is used by a different instruction for the load, we can use register R5. That allows us to move the instruction above down below the load, and then we'll also be able to move the instruction at the bottom up. And so now we can create two spaces beyond the load for the load to happen. Many out-of-order processors will actually perform this kind of register renaming dynamically in hardware. Basically, they have extra physical registers that aren't available to the programmer that they can use as temporary storage spots in order to execute instructions out of order without violating these anti and output dependencies. Now, loads and stores are expensive, so compilers try to keep as many values in registers as possible. However, there's a finite number of registers on each architecture. And so the many variables in a program have to be allocated to what is often a smaller number of registers in a way that hopefully minimizes delays from loads and stores. Section C5.2.2 in the text has a brief overview of register allocation, and that's covered more in depth in section C17.8. And we'll talk about it in the lecture from section 17. What's important to know right now, though, is that register allocation and instruction scheduling interact, because if we want to increase instruction level parallelism, we have to have instructions that are independent of one another, and so that may require more data to be in registers at once, and then the register allocation problem becomes more challenging. Let's check our understanding. So to sum up our conversation about architecture, we've learned that memory takes more time to access than registers, especially when there's a cache miss to memory. And cache hierarchies are able to speed up access to memory over what would take if we went to main memory. Modern processors execute instructions in a pipeline, which speeds execution, but increases the need to generate code in a careful way so that we don't have stalls in that pipeline. Recent processors provide concurrency through multiple cores and hardware accelerators for graphics and other tasks. Instruction scheduling can avoid pipeline stalls and increase the instruction level parallelism, allowing programs to execute more efficiently. Register allocation is helpful as well because it can reduce traffic to and from memory. Programmers also contribute to efficient code by writing algorithms that can better exploit cache locality and the available parallelism that the hardware provides.